Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing. Testing on YouTube. I think it's like this. Looks good to me. All right. Testing on X. Let's go to X. Starts in 1 minute. Blow my nose real quick here. It's probably the anti-ASMR right there. All right, I think we're live. It literally starts with me blowing my nose. Perfect. All right. Let's get started. Let's actually close out of this OBS here. Welcome everybody to another Hoopo stream. This one is called Feast. So we're going to be going into some papers today. Recently, you can see here, June 21st to 25th, there was the Robotics, Science, and Systems, otherwise known as RSS conference. And we have some award papers. So these conferences generally have these different types of awards. You can see here there's a couple different categories. So we're going to be looking at the winner of each of the 4 categories. So we have outstanding demo paper, outstanding systems paper, outstanding student paper, and then outstanding paper. So the winner of the outstanding paper is this one here, Feast, a flexible mealtime assistance system towards in the wild personalization, and that's where the name Feast comes from. We're also going to be looking at some other papers. So the winner of the outstanding student paper, which is this one here, solving multi-agent safe optimal control with distributed epigraph form Marl. Quite a mouthful on that one. Then we have outstanding systems paper, building Rome with convex optimization, this one here. And then we have outstanding demo paper with demonstrating Mujoko playground. So those are the 4 papers we're going to be looking at today. I didn't attend this conference. I didn't have any research in this conference, but, you know, it's always good to kind of see what's going on in these conferences. I think going to conferences is a little bit overrated, you know. You have to travel, you spend a lot of time. I don't know. I don't think it's necessarily worth it unless someone else is paying for that. You know, maybe your company is paying for that. Maybe your college or university is paying for it. But I think you can get 90% of the conference just from reading the papers yourself afterwards. So we're going to start with this one here. This is the one that won. And this is a very wholesome paper. So it's a very tangible real-world paper where they actually deploy a robotic system for assistive feeding. So you can see here this is a 7-DOF arm feeding this guy. You can see here they have multiple different participants, and the robot is doing it. Look at that. It's actually feeding them. So this isn't like necessarily a new concept. People have been doing this for a while, you know. This kind of like assistive robot tech. But you can also think of it in that way as a kind of a benchmark, right? So you can compare the kind of assistive feeding tech that we had 10 years ago, 20 years ago, and you can see how every single generation it gets a little bit better, it gets a little bit more robust. It's still using a lot of the classic robotics, right? So you can see this mug has a little April tag, which is how you can get the exact 60 pose of an object, right? So even though April tags are decades old at this point, and we have modern convolutional neural nets, that can do things like segmentation, pose detection, key point detection. Like all of those can be done with a deep learning approach, but you just can't beat the April tags. The repeatability and accuracy, as well as the compute required to get that repeatability and accuracy, is just unbeatable for these April tags. In fact, we even saw them at the Keen Technologies demo, which was John Carmack's demo. This is the famous Doom developer. He's in the RL world now. He's doing Atari, but he's doing it with a robot system. And actually, you could see that he's also using April tags. So I make use of April tags as well. So on my Tapbot project, I use these April tags, put them everywhere. So it's always interesting to me to see these classic robotics approaches continue to be used way into the future just because they're just very good. Okay, so let's read the abstract for this paper, and then we'll go into some of the figures, and we can talk about some of the stuff here. Physical caregiving robots hold promise for improving the quality of life of millions worldwide who require assistance with feeding, and not just the people who require assistance with feeding, but I think this is going to be the future as well, right? So you can imagine a future where, because of the inversion of the demographic period, we're going to have more, or demographic pyramid, we're going to have more and more people that are older, and eventually at some point, once you start putting in neural links, you start putting in everyone living in these kind of VR worlds. I think this kind of idea of a robot feeding you is going to go from being something kind of novel and unique to just disabled people to something that pretty much everyone has, right? So maybe in the future, we're all getting hand-fed by robots. But in-home meal assistance remains challenging. There's a bunch of different issues, right? It's the kind of the difficulty of doing something in the real world with a robot. You have all these problems that you don't have to think about in your perfect academic kind of theoretical world. But if you're going to actually do a demo like this, you actually have to figure out how to solve them. So the 3 key tenets for in the wild: personalization, adaptability, transparency, and safety. Feast, which is the system, is a modular hardware that enables switching between assisted feeding, drinking, and mouth wiping. It has diverse interaction methods, including a web interface, head gestures, and physical buttons to accommodate the diverse functional abilities and preferences, and it is parameterized by behavior trees that can be safely and transparently adapted using a large language model. So this is the most interesting part to me, the kind of like end of it here. That's a very interesting way to modify the behavior of a robot. But we're going to start with this, just the hardware, right? Because they had some good ideas there. So the actual end effector, and you can see it here, this is the website for this. The end effector has multiple different end effector or tools, sometimes they're called, that you can use, right? So you have a kind of a fork or a spork kind of thing. You have a gripper to pick up the mug, and then you also have this wiping tool. So having different tools like that, you see that sometimes in industrial use cases, but that's a whole kind of rabbit hole that you can go into in the design of the actual tools, such that the interface between picking it up, you want some amount of repeatability there, right? You don't want, whenever you're grabbing something with, say, one of these high degree of freedom articulated hands that we see now, you're going to get a lot of variance in kind of the relative position of the tool to the hand. So something like this, having locating features, so something on the actual mechanical design that makes it so that every time you grab it, it ends up in the same position. Perhaps adding April tags like they did here, so you know the exact relative position of the hand to the tool. There's all these little tricks that you have to do, and one trick that they point out here, which is actually very interesting, is this idea of safety-centric hardware where the end effector with the spork has a weak point specifically on the joining of the spork to the end effector. So this is something from car design, right? But whenever people design cars, they explicitly design what's known as this crunch zone, where the front of the car will compress before the rest of the chassis compresses. And the reason you do this is because rather than kind of trying to make every part of the car as tough as possible, you design a specific part of the car so that it is less tough than the rest of the car, which means that if the car ever gets into a safety situation where it is starting to get destroyed, you know which part of the car is going to get crushed, right? So that's the whole point of having this crush zone in the front of the car, because like that, you kind of know that the front of the car will impact or will absorb that impact and break, and it won't hopefully not transfer that force into the areas where the humans are. So a same kind of idea here with the end effector, where if the robot, something happens with the robot and you have this spoon and you're trying to put it in this person's mouth, right? You really don't want the weak point to be such that the spoon gets driven into the person's mouth and you just kind of stab the person with the spoon. So by having this weak point right where the spoon connects to the end effector, that means that even if there's some weird situation where the robot does some movement and it can potentially hit the human, it'll break the spoon off, right? So I thought that was a very clever design decision there of having this kind of built-in weak point. Yeah, here it is, the safety-centric hardware. You have the e-stop, right? So if you're going to have a real robot, having a big red button where you can hit it and the robot stops, that's kind of becoming a standard. It's been a standard, but I'm glad to see it continue. All right, let's look at some of these figures here. Comparison between Feast and other mealtime assistance systems. Let's see if they can, what's the earliest reference they have here? Park et al. 25. This is a 2020 paper. Okay. What about this one here? This is another 2020 paper. So these are all relatively recent. Feel the Bite. This is a 2024 paper. All right. I think all of these are going to be pretty recent. 2024, yeah. I guess there's literally that many papers. You know, even myself as a robotics person who enjoys reading papers, look at that. I'm unaware of the literally like 6 or 7 other papers that are identical to this. I've never even heard of these, so it just kind of goes to show you how many papers there are nowadays. All right. There was a couple other things that I highlighted here. So this part here, skills as parameterized behavior tree. So a behavior tree, let's pull up a picture of that, is a graph, right? A tree, right? Where you have nodes, root nodes that split up into leaf nodes, and then you can organize the state machine of the robot into this, right? And this is not even just used for robots. This is also used, for example, for the NPCs in video games. Generally, the AI for an NPC is implemented as something like a behavior tree, right? Where you might say, okay, if you're in this state and you have this specific condition, you go down into this leaf node and you execute this. Maybe you loop this behavior. If you're here and you have this specific condition, then maybe you execute this behavior, right? And the design of these behavior trees, there's lots of software that kind of already perfected this, right? This is something that people have been doing long enough that these behavior trees have gotten quite robust. I think there's various different versions of these built into ROS as well. But the interesting thing here that they do in this paper is this idea of using a language model to adjust the node parameters, right? So all nodes and parameters are given human-readable names and descriptions to facilitate LLM-based adaptations. So, for example, the speed can be low, medium, or high. Time to wait before auto-continue, 5 or 100. These would all be kind of hyperparameters that you would have to set as a human, right? So as a human, when you're designing this behavior tree, you're deciding, okay, after detecting a specific thing, how long do you wait before you decide that that detection doesn't count anymore, and then you go back up to the previous root node in this behavior tree, right? Or how many times do you execute this specific behavior before you decide that, okay, after try number 3, you should go back and then maybe do a calibration behavior or something like that, right? You would have to design all of that yourself, right, with your human intuition, and then over time you would tune it as you experiment with the real system. But this idea of using an LLM to modify that, I think that's a very great idea. I'm actually probably going to steal this for my tattoo robot, right? 87GN, cheers. How's it going, man? I don't even know if you're a man, so how's it going, friend? How about that? Feast users can make personalization requests through spoken or typed language. The natural language request is converted into structured behavior tree updates using an LLM. I think for this, they're still kind of using the two-part kind of system here, where you have a text-to-speech or speech-to-text. So you speak, converts that to text, and then the text is fed into an LLM. You can see that here they're using GPT-4o. But I don't think that's going to necessarily be the paradigm forever. You know, I think that we're starting to see voice-based systems that are a little bit more end-to-end. So I think that's going to go into robotics, right? I think pretty much all the robots nowadays, all the voice stuff for robots is the text-to-speech or speech-to-text into an LLM. But I think that's just an intermediate point. I think we're going to eventually move to this kind of more end-to-end where the audio is coming in audio waveform format, not being converted to text. But will behavior trees still be a part of that? Probably. Because I think the behavior tree is important for safety, right? It's kind of like how you have the e-stop, right? Will we always have mechanical red button e-stops? Probably, right? You can imagine even the humanoid robots, you're going to have a red e-stop on it, right? I don't see a situation where you ever have an e-stop. And same thing with the behavior trees, right? Just for safety reasons, knowing it's kind of like almost like a interpretability kind of thing where it's like you know what state the robot is in and what it was trying to do, right? And in a full end-to-end system, you don't really know exactly what it's trying to do. You know, it's a little bit more nebulous. So I think that even if we have these end-to-end robots, there's going to be this idea of a state machine or a behavior tree that allows you to then go back in retrospect, in hindsight, and say like, okay, what was the robot actually trying to perform at this specific point in time? Maybe it just becomes kind of a conditioning vector. So you have a full kind of end-to-end robotic system that's all a neural net, right? This kind of executing blindly this neural net. But there's a kind of a state description vector that includes the actual part of the behavior tree that you're in. Like Moshi, yeah, that's another good example of this kind of end-to-end system. This, I think we actually even Moshi speech model. This one here. Yeah, I think we actually did a stream on this one as well, but you can see here it's consuming the audio input as a waveform, right? And actually the way a lot of these audio input ones work is they actually turn it into an image. So they use these like MEL spectrograms to turn it into an image, and then they actually consume it with a convnet. There's also a different design where they have a kind of a 1D convnet, but I don't exactly remember which one this is. But you can see how it's end-to-end speech, right? So why not just make it, instead of outputting speech here, it also outputs robot actions, right? So the same way you can kind of take a diffusion model known as these action experts and kind of staple them onto a vision language model and call it a vision language action model. I think you're going to see a similar thing like this, right? Where you're just going to be able to take one of these action experts and just kind of staple it onto this type of system, and then you can go straight from audio input to robot actions. How's it going, little Cam? So it's been a while since I did a paper stream, I feel, so just to kind of give you guys ideas of the colors, I do yellow is just for generic highlights, and then I use purple for the hardware. So here's the actual hardware that they're using. You have a Intel NUC, and a 16 gigabyte RTX 4090 GPU laptop, which is actually the same one that Carmack used. So kind of interesting that everybody's using laptops. I'm using a laptop too, so I have this is a slightly different one, but I have the same exact hardware in my tattoo robot. I basically have one small CPU heavy machine, which is this Intel NUC, and then I have a separate kind of GPU machine. At this point, I have two. I have a laptop and I have a AGX Orin. But in this one, they just have the CPU machine and then the GPU machine. Carmack, for this demo, I think only uses the GPU machine, but they also have this small CPU machine, but it's mostly just for some overlay. Yeah, they have like a little Raspberry Pi, but I think this is just to take the input from the Atari, which is probably some like super outdated like serial based input, but you know, good to see a confirmation of that, right? These like multi compute node robotic systems kind of becoming the standard here. Let's see what else. Here's the utensil design. Actually, we can kind of zoom in on that right there. Utensil motor control module encased. You have the RealSense D435. RealSenses are just really popular right now. It's kind of, I'm a little disappointed because I have RealSenses on my tattoo robot and they're honestly kind of a nightmare. And they've been a nightmare for such a long time. I've been using them kind of ever since I got out of, when I did my robotics masters at CMU. That was like almost 10 years ago. And we were using RealSenses back then too, and they were still shitty, right? So it's like these structured light sensors, they're just not very good. They are very sensitive to the lighting. They're also sensitive to the actual material that you project them on, right? Because they're relying on this infrared light kind of reflecting and that allowing you to determine the depth. But if you're projecting this infrared pattern onto like some matte black non-reflective surface versus something like this, which is a reflective black surface, right? So even just the difference between the front of my cell phone and the back of my cell phone, that's a huge difference for these structured light sensors. But even that, which is kind of a fundamental issue with the technology itself, there's also just the more practical reality that these RealSenses are kind of the limit of how much power you can draw from a USB port. So they all have this issue where they're just constantly dropping out, right? When I run my tattoo robot, the thing that fails, like the weakest link in the chain, is actually the RealSense camera. A lot of times it'll run straight for 15 minutes and then the RealSense camera stops responding. So I don't know. I almost want to get rid of these. I wish someone made a better version of these. I guess Intel is. They're definitely putting effort into these RealSense cameras. They're getting more people on that team. They're kind of promoting them more. You're seeing them more in different robots, but I just feel like there's still so much room to improve the kind of camera and video modules of robots, kind of make them much more robust, maybe use better technology. All right, we have a Robotique 2F85. That's the actual gripper here. You can see it's actually doing kind of an inverse grip, so it's not gripping the tool. It actually kind of extends into the tool, so it kind of like opens it like that, which is a good way of kind of ensuring, right? This is kind of what I was talking about with these mechanical locator features, where it means that if you grip this, no matter how you grip this, the design of it ensures a specific orientation of the end of the tool with respect to the end effector, right? You have a force torque sensor here. So those are also kind of not super great. There's a bunch of different force torque sensor manufacturers. This is basically, there's different ways that you can get the force on a robot arm. You could actually look at the motors of the arm itself, right? And you can look at whenever the current goes higher, that means it's kind of pushing against something, and you can use that to kind of get an idea of how much force is being applied at the end effector. But those techniques generally don't work as well as the explicit force torque sensors, where you just put this little puck in between the end effector and the tool and the actual mounting point for the tool. But they don't work super well either, right? So it's kind of, you can see here, here's the actual cable that comes out of that force torque sensor. I don't have a huge amount of experience with this specific one, but just every single time I've used those, they've never been that great. All right, here's the skills. So these are the different nodes inside your behavior tree. So you have something like pick tool, you have place tool, you have acquire byte, you have transfer tool, you have emulate transfer, and you have retract. Interesting. All right, let's see this. Meals fed to care recipients. All of these look pretty pretty small. I don't know, that's all I got to say here. All the different pieces of food are very evenly sized. So they're definitely trying to solve a simpler version of this, right? Imagine how much more difficult this is going to get, because there's some pretty complicated foods to eat. Like, think about eating something like a fish, right? That has like the bone still in it, right? Even chicken with a bone, like a rotisserie chicken with the bones and everything, and like trying to like pick that apart, that's actually a very high level manipulation problem. So in terms of real world robotics, we're still just solving kind of the super basic manipulation problems. Frustration, what does that mean? Okay, see this. Okay, I think that's most of it. Like I said, it's not super novel kind of algorithmic paper. This is kind of a real world implementation, almost like a demo paper, you know, where it's like, here, this demo is super cool. It's super wholesome because you're like helping these disabled people. But these papers are always interesting just to kind of get an idea of like, okay, where is our technology actually at? And what are the shortcuts that we're still using? What are the techniques that we're not using? So like, for example, notice that they don't really use any reinforcement learning here. I don't think so, but because it's not really going to get you a better outcome. I think there was one thing I wanted to point out here as well. Down here. Yeah, but they mentioned the stand that they're using, and they're using this one here from Vention, UR5 heavy duty mobile stand. 2.5K for this is such a ripoff. I feel like you could make this for less than 1,000 easy. So I don't know, if you're gonna, I think it's like the reason they do that is because most of the people that buy these are kind of enterprise, so they don't really care between the difference of like making it yourself for 1,000 or buying it for 2.5. But 2.5 for what is effectively just a bunch of aluminum framing and a battery just seems like kind of a ripoff. How's it going, Patrick? Hola. All right, let's move on. So the next paper we're looking at is this one here, demonstrating Mujoko Playground. You got the original Mujoko guys here, like Yuval. You got some robotics royalty here, like Peter Beal. Google DeepMind, University of Toronto, University of Cambridge, UC Berkeley, right? Lots of different academic institutions here just because everybody uses Mujoko, so very easy to get a bunch of different people to work on a Mujoko paper. This is also a very short paper. You can see here not a lot of, the paper itself is like 7 pages. But mostly, let's just kind of read through the paper because I feel like they describe it better than I'm going about to describe it. So, RL is computationally intensive, requiring an enormous amount of agent-environment interactions to train effective policies. So GPU-based simulations can significantly accelerate this process because the median GPU is far more powerful than the median CPU. While high-core CPUs exist, they are a little bit uncommon. And by keeping the entire agent environment loop on device, we can harness the high-throughput, highly parallel architecture, right? So here's a relevant tweet. This is from Kyle Morgenstein. This is another Austin-based robotics person that I've actually met IRL, kind of a cool guy, but he had a great tweet recently here. Sim plus RL is going to eat all the teleop plus imitation learning work alive once we can figure out how to generate diverse enough data. You just can't beat the scale, and we know how to do sim to real now, right? So what he's talking about here is a lot of people are working in this teleop plus imitation learning kind of paradigm, where this is a little bit kind of the robot is kind of based on this, where, okay, you have the real robot, then you have a human is going to teleop this real robot, and you're going to collect a bunch of episodes, and then you're going to do imitation learning on top of that, right? We're going to take some either model and train it from scratch like an ACT, or you're going to take some pre-trained model and then fine-tune it on that teleop data, right? That's a little bit different, although very similar to Sim plus RL, which is what people use, for example, a lot of these humanoids, especially the walking policies, the get-up policies, like those type of things here in these examples, the sit on the box, like those are generally trained almost entirely in Sim, right? So basically you have a perfect simulation of your robot, right? All the different lengths, you have all the different moments of inertia for all the joints, and then you have a reinforcement learning system effectively start from scratch. So first the robot's just kind of flailing around, and then in that random exploratory flailing, you sometimes end up in a slightly better position than random, and then those end up getting reinforced, and then once you kind of slowly over time reinforce more and more and more and more, right, you can kind of see the system go from basically complete garbage to something that actually kind of works pretty well in your simulation. And one of the biggest problems with Sim plus RL is this Sim to Real, right, where your reinforcement learning system will get very good within the simulation itself, but then when you try to take it into the real world, it doesn't perform anywhere near as well, right? And some people thought, or the kind of narrative has always been that this is kind of an unsolvable problem, but more and more we're seeing that it's not actually unsolvable, that in fact there's a very simple solution to this, and that's the idea of domain randomization. So the Madrona MJX is basically just Mujoko, but on the GPU, which can effectively do your simulation and the agent itself all on the device, right? So that's the simple idea here is that you take the Mujoko sim and you run it all on your GPU, so you can do it all on the GPU, right? So we build upon Mujoko XLA, a JAX-based branch of the Mujoko physics engine that runs on the GPU, enabling training directly on device. But the important thing here is that the Madrona MJX integration also supports customization of each environment instance, allowing for domain randomization of visual properties such as geometry, size, color, lighting conditions, and camera pose, which are crucial in sim-to-real transfer of vision-based policies. So what this means is that when you're training in these simulated environments, right, you're not just training on, first of all, you're not just training on one environment, which is what you would be doing with a CPU, right? In a CPU, you're basically just kind of doing this a little bit more in a serial fashion. You're just doing one, and then the next one, and then the next one, and then the next one. And your CPU can be pretty fast, but that's going to be way slower than the kind of parallel computational paradigm of a GPU, right, where you're doing lots of these in parallel. But doing lots of them in parallel isn't going to be that useful if all of your environments are the same, right? So if in every single one of your environments, the robot links have the same moments of inertia, then you're going to be really overfit to the specific moments of inertia in Sim, which are not going to be the same as the moments of inertia in the real world, right? So the ability to randomize those, right, where, hey, in every single instance of the environment, we're actually going to have a little bit of a difference in the geometry size, right? So maybe one leg is slightly longer in this instance, and then in this other instance, it's the other leg that's slightly longer. So whenever your reinforcement learning agent is learning, it'll end up at a policy that is robust to the length of the limbs, which means that whenever it actually gets deployed in the real world and the length of the limbs is some other random configuration or permutation because of just the way these things are manufactured, they're not always going to be perfect, right? Maybe whenever this part got injection molded, there was a little bit more accumulation of mass here, which means that the moment of inertia of this leg is slightly different than the moment of inertia of that leg, right? Which is actually going to happen more and more. I think that there's going to be such a pressure to manufacture these things very cheaply, right, that you're going to get a lot of variance within the actual robots themselves, right? So the there's going to be advancements in kind of repeatability and kind of high precision manufacturing for sure, especially once we start putting robots in factories. But I think that the robots are gonna get so cheap that it's going to be very likely that the robot that ends up in your house is going to have like one leg that's slightly longer than the other leg, right? By millimeter, I'm not talking like centimeters longer. I'm talking about like millimeters, but those millimeters make a difference, right? So domain randomization per environment instance, accelerated on a GPU, is going to be a very powerful way to make SimRL solve the sim to real gap. And if you can solve the sim to real gap, which we're basically already seeing a bunch of evidence for, right? So look at this. This is a real robot. Like pretty much all these Unitree demos are sim to real existence proofs, right? They're just showing you that this sim to real approach works. So I do agree with Kyle here that sim plus RL is going to eat the teleop plus IL work alive. I don't think the teleop plus IL is like dead. I think there'll still be a place for some amount of teleop, but I do feel like teleop is just kind of an intermediate point in the technology stack as we ramp up. I think eventually the way you're going to see it is that the robot is trained entirely in sim. And not only that, but the robot is designed in sim, right? So one thing that we don't actually see yet is that the reinforcement learning is only being used to tune the policy, right? So you have a policy, which is just your neural net, and there's weights on that neural net. And fundamentally what the reinforcement learning is doing is it's changing the weights of that neural net with the experience that it's collecting in sim. But technically, the length of the arm, that's also differentiable. You could also push gradients into the size of the hand. You could push gradients into the distance between the eyes, right? So all these different kind of hardware parameters, you could envision a world where we're using reinforcement learning to actually optimize those as well. And I think that if you're looking at 10 years in the future, it could be that most of our robots aren't even designed mechanically by a human. They're kind of designed in simulation, and then whatever ends up happening there, whatever number of fingers, whatever length of the arms and relative position of different things that the RL decides, that's what the robot ends up looking like. How's it going? Patrick and Kyle Duz. 87GN. Shouldn't only the parts that matter and the forces at the output of the ground? I was under the impression that the rest could just be then solved with just kinematic equations, positioning each arm and leg. You can do that. I mean, I kind of did some of that, right? That's actually like the very first paper I ever did was specifically on this, right? Can you use just kind of like inverse kinematics and kind of just geometry or geometric mechanics to determine or to create effectively the correct force at a contact point such that you create a desired movement, right? So I did it for a snake robot. So like what joint do you put at each of the, or torque do you put at each of the joints of a snake robot such that it pushes off of the specific contact vectors on the ground and produces a specific motion, right? You can envision doing that with a humanoid. Okay, there's these specific contact points. How do I need to distribute my mass? Can I create a system of equations that I can then just solve in order to get the specific vector of force and movement that I want? And you're not wrong that theoretically you can do that, 87GN, but it just doesn't work very well, right? This is kind of like the classic control problem, and we tried to do that for decades and decades and decades, and it just kind of never really got anywhere, right? You can think about the Asimo robot, right? Asimo Honda, right? Like that was entirely controlled using these methods, right? This is an ancient robot at this point, like kind of like 90s, 2000s, right? And there was no deep learning, like people weren't using neural nets inside this robot, right? But it was able to walk and move, and all of that was this kind of classic control that you're describing, 87GN, where it's like, okay, we know exactly the weight of all these things, and everything is tuned, and we have this perfect model of our robot that's just basically based on Newton's laws of motion of, okay, you have mass and then you have this moment of inertia, but it's just very, very brittle, right? that type of control algorithm just doesn't work super well. If there's anything wrong with the robot, it doesn't work very well. Every time you go to a different type of floor, right? So here it's on like a shiny kind of sticky floor. Maybe when it's at the hotel, it's on a carpet, right? So as soon as you change any variable in there, it's very, very brittle, very fragile. It doesn't work anymore, right? Versus these reinforcement learning policies, especially the ones that are trained in these domain randomized sim environments, they're much more robust, right? And that's why you can take these robots and you can just kick them, and they kind of figure out how to stabilize. Versus this Asimo Honda robot, if you kick this robot, there's 100% chance it's falling on the ground. All right. Here's the different humanoids. So part of the sim environment. So there's kind of like a war going on right now in the simulation frameworks, right? You have a bunch of popular frameworks here. I think they list a bunch of them actually. Right here. I think it's here. But you have Isaac Sim. Yeah, Isaac Sim and Isaac Lab. You have different physics engines, MJX, Brax, Warp, Tai Chi. Mujoko is there, right? You have Many-Skill is another one that I've used before. You have all the different game engines can also be used to kind of do this kind of robotics-based sim learning, like Unreal Engine, Unity. There's a little bit too many of them, right? It kind of feels like the early part of the Cambrian explosion, where there's a lot of different sims, a lot of different implementations of effectively kind of the same tech stack, and it's not entirely clear which one is going to win yet. So for a team like the Mujoko team, which I think at this point it's kind of a distributed group, right? It's not like a centralized team working on Mujoko. It's an open source software, so at this point there's a lot of different people that are working on it. One of the best ways to get people to use your specific simulation stack is to basically have all the different robots integrated into it, right? And this is what we see with the Many-Skill stack as well. This is one that I've contributed to, just a very small contribution. But you see they're also trying to show you that, right? So here's look at all these different robots, right? So the more robots that you have that work in your specific simulation stack, the more likely there is people are going to work on it, right? So like if I work on quadrupeds, and I'm interested in Mujoko, and I go and nobody's integrated my quadruped into Mujoko, probably not going to use Mujoko, right? So it's in Mujoko's best interest to have quadrupeds there, right? So pretty much all these different RL sim stacks, they are racing to kind of just have all the different robot morphologies and embodiments in them and already set up so that you can adopt them, right? So they're kind of, in a way, you can think of it like they're subsidizing the integration cost, right? There's some integration cost to taking your new robot embodiment and putting it in a robotic simulation. And if that integration cost is high enough, you're not going to use the simulation. But if the people who make the simulation do that integration for you, and generally they can do it much better because they understand the simulation, they know all the nuances of it, then you don't have to pay that integration cost, so you're going to use this simulator. So I think that's one of the main kind of vectors of competition that you're seeing in these simulation stacks, is just how many different robot embodiments do you have. Okay, a couple more interesting things here from this paper. Policy operates at 20 hertz. So these are all just like one-off numbers, but whenever I read these type of papers, it's always interesting to me to just kind of get an idea of what people are using, right? It's always very interesting to me whenever people tell exactly what's your control speed, right? Are you at 100 hertz or are you at 20 hertz, right? So 20 hertz, that kind of is about what we expect, right? We go back to here. What are you using? 16 gigabyte NVIDIA 4090. Okay. What are these guys using? 2 RTX 4090s. Okay. What about this? 1 RTX 3090. So on inference on an RTX 3090, so 15 hertz. Training on 2 RTX 4090. These are all, you could do this at home, right? That's kind of the vibe I'm getting, is that none of these are, I don't see any H100s here, right? I don't see any 8 by H100s, 100 by H100s. They do have 8 by H100s here. But, you know, it seems very approachable. Optimization of topology-specific hyperparameters as future work. So topology is just a fancy way of talking about your compute that you're training or performing inference on, right? So, for example, one H100 versus 8 H100s, that's a different topology, right? The connections between the 8 H100s and the 1 H100s and the two 4090s, right? There's different, you can really, if you try to think about, okay, instead of just thinking about it as two 4090s, think of it in kind of a graph, right? Think of it kind of like this, right? Imagine it as a graph where you have like the specific chips inside the 4090, the specific memory caches in the 4090. Going from one 4090 to the other 4090 is actually quite slow, right? You have to go out into the CPU, then across the network, then back into the CPU, into the GPU, right? So there's this kind of nuance to each individual computational platform, which is known as the topology. And the hyperparameters for training and performing inference are topology specific, right? So 8x H100s in some specific configuration is different than 8 H100s separated into 8 little CPUs connected with a kind of a router, right? So like ideally you're tuning these different hyperparameters such as the number of parallel environments, right? So how many environments are you running in parallel to collect the experience, right? The reinforcement learning loop is basically collecting experience, then training on that experience, then collecting experience, and then training on that experience, and then collecting experience, and then training on that experience. That's online reinforcement learning. Offline reinforcement learning is similar, but you've already done all the collection, so you kind of collected all the experience, and now you're just training on that collected experience. But on policy RL, it generally works way better because you get experience that is specific to the RL policy that you just trained, right? So like you collect a bunch of experience, you push that into the policy with your RL, and then now you can take that new policy, which is going to be slightly different from your previous policy, and you can use it to collect more experience. So the problem with on-policy reinforcement learning is that you have to be constantly updating and then collecting more experience, right? So the advantage of off-policy RL is that you could just have all this data and then you train on it. With on-policy RL, you have to be constantly recollecting data as your policy adapts, right? Which is what, for example, not this. I guess we went back. This one here, right? That's what Carmack is doing here. This is on-policy RL, right? So he's training the policy on experience that is collected with the policy that is about to receive the gradients, right? So this is on policy RL, right? But where was I going with this? Oh yeah, so the reason I was talking about on policy versus off policy is that there's a bunch of different hyperparameters there, and those hyperparameters are going to depend on the hardware that you're actually training on, right? And actually, one interesting thing that Carmack mentioned in this talk is that he's literally known as the kind of like a programmer god, right? So like he literally mentions that he is actually one of the first people to write code specifically for a GPU. So he was one of the first people to kind of develop these 3D games, and he wasn't just like some manager type or like some kind of like yapper, you know, like who doesn't actually know the tech. He like literally is the person who figured out how to create 3D graphics using the first GPUs, right? So some of the first GPUs that came out, he's the one who figured out, okay, how do you actually render this pixel here and the pixel in the wall in the background? So this guy knows how to use hardware. And at one point in this talk, he mentions that he has the entire reinforcement learning loop as one coup de graph, right? So like he's done the entire like inference collection and then training in one giant, effectively you could think of it like one big fat CUDA kernel that does the whole thing. So it's like that's actually kind of, I feel like that's a very good idea, right? Because it's like there's no reason you can't do that, right? You could actually figure out some way to do the entire on policy RL process in one kernel, right? One graph that you don't need to be transferring stuff out of your GPU into the CPU, then back into that. Most people don't do that, right? Most on policy RL, maybe you have one GPU that is being used for inference, and then you have a different GPU that's actually being used for training, and they're executing different computational workloads, and they're communicating by sending data, right? Maybe storing it in some hard drive in an intermediate place, right? So like the ability to do all of that on device, as they say here, that could be a huge unlock. So that's part of the story here with this Mujoko playground as well. Is like, can we fit the entire RL loop on device so that we don't have to be kind of like storing things and putting experience, and then having this idea of like the concept of a replay buffer, which is a terminology from the RL world where you have basically like think of it like a bucket, like a hard drive that's just storing your stuff, and you have all this complicated way of sampling experience from that replay buffer. Like, you know, maybe that complexity just kind of melts away, and you just have this kind of more kind of John Carmack, kind of like one giant CUDA kernel that does all the on-policy RL just in one big fat just blast through your GPU, rather than kind of these complicated kind of multi-component systems. How's it going, Aries? 87GN with a question here. So we wrote the whole thing on a custom driver level. Pretty much. I mean, I don't actually know. You know, it's not like they didn't open source anything as far as I think they're going to open source this code. But yeah, if there's someone who can write the entire an online reinforcement learning loop entirely in CUDA, it's fucking Carmack. So I could definitely not do that. It's like that's beyond my level of technical ability. But you know, that's kind of what you get, is that sometimes, or a lot of times, you know, these little niches of technology, which deep learning and robotics was its own little niche, progress is a little bit limited by kind of just how many people are even working on it, right? And then once that thing becomes very popular, and you kind of have this this effect where all these external people come and start working on it, right? Their expertise that they've built in other parts of the tech world now suddenly gets applied to this, and you get a lot more progress really quickly, right? So reinforcement learning for a long time was just this kind of like niche corner of academia, you know, where you just had maybe like on the order of 1,000 people working on it every year. And now all of a sudden you have like 10 times that amount of people working on it. And you have people working on it that are very experienced in different things, such as kind of more like low-level software kind of people. So you're going to see a lot of progress really quickly in the RL world, especially RL for robotics, as you have kind of all this influx of like experts from different parts of the tech stack coming in and now suddenly applying their intuition and their experience and their expertise to this particular problem. So expect a lot of progress very quickly. And if we get a lot of progress very quickly in simulation, in online reinforcement learning, again, I just feel like this tweet is very prescient, where I feel like we might see the simplest RL, which is a much more scalable stack, right? So if you go back to the kind of bitter lesson, Rich Sutton kind of mindset of like, okay, the bitter lesson from Rich Sutton is basically a perspective that you can take, and it allows you to evaluate which methods are going to work best. And if you have a competition between two different methods, and one method is way easier to scale than a different method, the one that scales is going to be the one that wins. So if we try to take that bitter lesson perspective on this fundamental problem here, which of these two is much more easy to scale? Simplest RL or teleop plus IL? Definitely simplest RL, right? Simplest RL, there's no human in the loop there, so you're going to be able to scale that significantly more than teleop plus imitation learning. So yeah, if I had to take bets, I would say that. Okay. Is there anything else here? They mentioned Genesis here. I think that was the one that we saw. That was kind of like hype, but it ended up not being that hype. Sheesh. How's it going, Ed? Let's go on to this paper. So we just went through the outstanding demo paper, and we started with the outstanding paper, which was Feast. Now let's do the outstanding systems paper. So this one's called Building Rome with Convex Optimization. This is out of MIT Department of Aeronautics and Astronautics. And this is a drone paper. So basically in this paper, they have these little drones, and the drones are effectively doing kind of like path planning, like multi-agent path planning of like, okay, you have this obstacle. How are all these little drones going to move through this doorway, right? So that's basically roughly the size of a door. It's kind of like, okay, you have these killer drones. They're in a building. They're trying to fly to a specific target and blow up this person. Just to kind of use the most fucked up application of drones, which is the killer drones application. But that is one of the big applications of drones right now, is delivery of explosive payloads. But, okay, you have a bunch of drones that are, each of them has a little bomb, and they're all trying to get through this doorway to get into some person's apartment. How are they going into that doorway so that they don't hit each other? Right, and you can see that's kind of what they're doing here. They decide to kind of go one by one, right? How do you do that? So that's what this paper's about. It's multi-agent, safe, optimal control with distributed epigraph form model. So this paper is very, very math heavy. You can see just the amount of abbreviations here is insane. You have a constrained Markov decision process, a CMDP. You have multi-agent reinforcement learning, MARL. Let's do green. Green is for definitions. You have a multi-agent system, MASS. You have a multi-agent reinforcement learning, MARL. We already got that one. And we got centralized training, distributed execution, CTDE. Okay. So 8 different tasks across 2 different simulators, and then they also show results on real hardware. So within robotics papers, right, if you show results in sim, that's like this level. If you show results in sim and results in the real world, right, that gets you a higher level. So for these type of papers here that are going to win these awards, pretty much all of them are going to have the combination of both sim work and real robot work, right? So it's going to be very hard to win an outstanding paper award if all your results are in sim. So luckily, this is based out of MIT, so they have the talent and effort required to have results in both sim and real. But let's go deep. Let's dive straight into the deep end here. Okay. Problem setting and preliminaries. Multi-agent safe optimal control. So consider a homogeneous mass. So homogeneous in this case means that every agent is the same, right? So all of these drones, you can consider them functionally identical, although it would be very interesting to have a heterogeneous mass where you have maybe one quadruped, one humanoid, and like 6 drones, right? So you could basically extend this paper by having a multi-agent system with heterogeneous embodiments. But in this one, it's a homogeneous mass with n agents, so n drones. At time step k, and as soon as you have this idea of time step k, right, so like you're discretizing time, right? So that's why this is a Markov decision process, right? As soon as you decide that, hey, time is no longer continuous, which according to our best ontology right now, which is the Einstein's relativity, time is continuous. I'm not necessarily convinced it is, right? My ontology is kind of based on Wolfram's ontology, which is based on this kind of computational kind of perspective where, okay, space is discrete and time is discrete. But as of right now, 2025, I would say most physicists think that time is continuous. So if time is continuous, as soon as you discretize time, now you're inside this Markov world, right? This MDP world. So as soon as we see time step k, okay, we're in a computational kind of MDP world. You have a global state and control input, so your global state x of k with some dimensionality n, and then you have your control input uk. So this is like, okay, the actual numbers that are used to control each individual robot, right? And then you have n of those because you have n agents. So each individual drone has some control vector uk, and then there's n drones, and because they're homogeneous, then there's they all have the same control vector. So you have u1k all the way to unk. Okay. And you have the same thing with the state, right? So the state itself is also the same for each of the drones. So you have this global state, global control vector. The multi-agent system problem is a general, nonlinear, discrete time dynamic system where you have some function f, which is taking the current state, the current control vector, and producing the next state. So the dynamics, which is basically just how does this system evolve under time, can be described by this function. This function is only a function of the state and the control input. So if you know the state, which is just kind of a fancy way of saying if you know the current state and if you know the initial conditions, right, and you know the input, then you should be able to determine what the next step is. We consider the partially observable setting. So partially observable is a fancy way of saying that this xk here doesn't contain all the information, right? So even though you have this idea of a global state, of, okay, here's the initial conditions, once you have partial observability, you're basically saying, okay, there's some other settings here that we don't have as input. So there's other variables in here that we don't know. So that's where POMDPs come from, right? So POMDP is a partially observable Markov decision process. Each agent has a limited communication radius r greater than 0. So this is kind of interesting. So one thing they could have done is they could have very easily said, okay, well, every agent knows where every other agent is, right? And this is something that you see in simulation all the time. So in multi-agent systems in simulation, you know where every single drone is because you have access to that, because you have access to the simulator. But in real-world systems, this drone might not know where this drone is, right? As soon as this drone is through the door, this drone here has no idea where that drone is, right? So you have this partially observable, partial observability from the perspective of each individual drone of the other drones, right? So I think that it's a very it's a something that they didn't necessarily have to add, but the fact that they added it is what makes this paper great, right? So like those little decisions there of like, okay, let's actually put results in the real world. Okay, let's actually add this limited communication radius. Like, right, those things just make it harder, but adding that into your paper is why you get the best paper award, is because you just choose to make it harder. Denote this as the vector of the information observed by the agent I. Okay, so basically what you're saying here is that you have your state, and then your O of I's, your observation, are some function, some mapping of that state. So like your state isn't actually what you're getting. It's not what you're using as input. You're using this O of I as input, right? And that O of I is related to your state, but it's not the same thing as the state. We allow multi-hop communication between agents, so an agent may communicate with another agent outside its communication region if a communication path exists between them. So that's pretty cool too, right? So, okay, the agents do not have kind of this oracle state knowledge of all the other agents. They have a limited communication radius, right? They only have partial observability of the global state of the system, but they have the ability to communicate with each other. So this drone doesn't know where this drone is, but it can talk to this drone, and this drone knows where that drone is, right? So that's a pretty cool little addition there. And you can almost imagine where this goes, right? Where you can actually start looking at this from like a information theoretic kind of perspective, almost like the going back all the way to like the ideas that Shannon had, where it's like, okay, I have Bob and Alice, and they're trying to communicate, and there's the information that they're trying to communicate, and then there's the kind of compressibility of that information. And if you kind of agree upon, okay, this bit that I send you has this specific meaning, and this other bit that I send you had this specific meaning, and that's based on the type of communication that's going to happen, right? So this, almost like how Morse code, the way that they designed it, specific letters that are used more often are compressed more. so that it's faster to send them over, right? You can start taking all these ideas and putting them into these multi-agent robotic systems that have limited communication, where, okay, what is the most common message that I'm going to have to send to each other, right? How can I take the most common types of messages and compress them more so that I can send them faster, right? So there's so much cool stuff to be doing in these multi-agent systems that have partial observability and limited communication. You have this idea of avoid-unsafe set. Okay, so there's some kind of global cost function or some function that constrains the possible control outputs, right? So this is where this word here, this constrained Markov decision process. Because what are the constraints here? Well, these are drones, and if they try to go lower than the ground, they're just going to hit the ground and explode, right? And if they try to move into an area of space that's already occupied by another drone, they're going to collide and then explode, right? So there is this constraint of, okay, you can't actually move here, right? So you're trying to solve this kind of path planning, but there's all these different constraints, such as, hey, this bubble of space is occupied by a different drone, so you can't actually move in there, right? And that's what these diagrams are here, right? Where you have the different drones. They're trying, so this is the drone is trying to get to that green circle, but there's these obstacles, right? So, okay, you have to be able to move here to that green circle, but you can't get into these obstacles, and then you can make the obstacles bigger, right? Bigger parts of the space are constrained, and then each of these drones themselves has a little bubble of space that they occupy as well. So that's where the constraints come from. Okay. So ultimately, what is the point here? The point is that you want a distributed control policy, pi I, that takes the observation O and outputs an action or a control UI, right? So why do they call it distributed control policy, right? So they have this idea here of centralized training, distributed execution. So the execution is, in fact, you can think of that like inference, right? So the execution of the control vector is at the drone itself, right? So the drone is executing just a little chunk of that global control vector, right? So if you go back to the way that they define this, right? So the policy is outputting this capital UI. Capital UI is the control input for all the agents, right? It's actually composed of a bunch of individual control vectors for each individual agent. So the policy is at a multi-agent level, but the execution is at the individual agents, right? And that kind of adds complexity. Yeah, and most of this is basically just kind of theoretical grounding and justification of their particular algorithm. But let's go down here. Yeah, like for example, distributed epigraph form model. Such a hardcore acronym there. But let's go to this picture because I think this one is this gives you the best idea of what's going on. Randomly sampled initial states and Z0 are used to collect trajectories in X and Z using the current policy pi. Okay, so you have your different robots, or different policies, I suppose. This is pi 1, pi 2, pi n. Each policy is slightly different. Data collection is happening. You're collecting this data. That data is then being used. This is your mean squared error. You have your centralized cost value function. This is the value function is what's actually, you could think of it like your loss function. And the same way that your loss function is used to push gradients into your neural net, in reinforcement learning, you have the same kind of idea where you have this value function is being used to basically push gradients into your actual policy. It's not direct, right? There's kind of actor critic. There's a little bit more complexity there. The terminology kind of gets a little bit unwieldy, but the basic idea, right, is that you're using this value function to change the weights in your policies with, in this case, PPO, which is just kind of like a standard proximal policy optimization, which is just RL, aka RL 101. And you want to maximize the value at each state, which is where that value function is coming from. Centralized training, That's what this orange dotted line here is. And then the green dotted line is this distributed execution. So the policy that you're getting from this centralized training, which is coming from the centralized value function, is then being distributed into each individual policy, right? So you see how all of these here have this Z, 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 and then once you get into this distributed execution, now you have this Z1, Z2, Zn. So now you have these different Z's here. Zik equals argmin Z, so the Z that is the smallest for this specific value function, right? So the Z that results in the lowest value, lowest cost there, that's the Z that you want to use for this specific policy, right? So that's how you're getting this distributed execution. I think we already mentioned this. They use PPO. They have a graph neural network backbone. So no transformers here, just straight up old school 2015 deep learning here. But the results are pretty good, you know? You're not going to have a best paper if your results are no good, and this one is pretty good. Like, look at that. So you have your little drones, and this one here, you can see that it has these red circles around it. So this drone has, it's basically taking up this volume of space here, and it's saying, okay, you're not allowed to move into these red areas here. And then all the other little drones, you can see how they're basically, not only are they avoiding the red circles of this drone, but they're also providing the kind of limited, you remember how I said the limited communication, where when the observation of one agent is blocked by the obstacle, another agent comes from another side and continues to observe the target. So now this drone, if it was executing a policy that was kind of scoped entirely to just this robot, right? So if it was multiple agents that were each running their own little individual policy, there's no way for the information here to be enough to execute the best possible control, right? Because it needs the information from that this one is observing. So you can see that's basically what happens here, is that this one, because it knows, you can see how it moves backward there. So initially it doesn't really know what's happening, but it sees what's happening from the other one, and then that is what allows it to move backwards. Right? So pretty cool stuff there. You can see the April tags. There you go. April tags yet again. Every single real-world robotics paper has April tags in it, is basically the reality of the situation. Right? Like I said, April tags here. Let's see. April tags. Look at that. April tags, April tags, April tags everywhere. They're just so fucking good. All right, so that's this one. That's the outstanding. Oh, actually, I think we got confused. That was the outstanding student paper. So we somehow skipped to that one. So now let's do the outstanding systems paper. This one. Building Rome with convex optimization. I kind of skipped this one. I'm sorry, guys. All right. Outstanding systems paper. This one comes from Harvard. Got two people here, Hao Yu Han and Hung Yang. This is a kind of like a SLAM SFM paper. Global bundle adjustment, scaled bundle adjustment. Let's actually go here to the introduction because I think this one describes it the best. So at the heart of modern structure from motion is determining the 3D structure from the motion. So you can see here, this red line represents the position of a camera in space. So it's like a cell phone camera, right? So that cell phone camera has some motion to it, and you're determining the structure of the scene from the motion of that camera, right? So that's where the SFM, structure from motion, comes from. And simultaneous localization and mapping, that's kind of another related kind of concept. I would say these are basically the same thing, but simultaneous localization and mapping is, okay, finding where you are in the scene. So like when you're right here on this red line, you know where you are, you've localized yourself in this 3D world, and you're also mapping the 3D world. So you're simultaneously localizing or figuring out where you are in this 3D world and mapping the 3D world itself. So that's SLAM. is based on the process of reconstructing camera poses and 3D landmarks from 2D image key points, right? So these cameras are giving you two-dimensional images, these RGB 3-channel images. Maybe there's a depth channel in there, but they're not going to be using the depth channel here. We're going to see why. But in a two-dimensional image, there's plenty of ways to get key points, right? So you can say, okay, this specific corner here, that's a key point. And then you can get a very similar key point on a different image. So now you have kind of this interesting thing where, hey, I can find the center of this table, this like center of this cross in both images. So now I have these 2 points in pixel space, these two-dimensional key points in 2 separate images. Okay, well, actually, I should be able to now use that information to figure out what the position of my cameras are, right? So that's kind of the fundamental intuition here, is that from these two-dimensional key points, you can reconstruct the 3-dimensional or 6-dimensional camera poses and eventually the entire 3-dimensional structure of the scene, right? Okay, so always making my Friday. Hey, I appreciate it, Max. Classical BA formulation. I would say, consider a so-called view graph. So again, this idea of a graph, right? We were looking at graphs from the perspective of behavior trees, right? We were looking at graphs from the perspective of a computational topography is a type of graph. And a cameras and points, in this case a view graph, is also a graph, right? So you have some camera poses. Here is poses in SE3, which is special Euclidean group 3, which is basically just the set of rotations and translations in time, or not time, space, 3-dimensional space, plus the rotations. You can see R1, the rotation matrix, T1, the translation vector. So this is the position of this camera at this specific point in the trajectory, right? Or it doesn't even necessarily need to be a continuous trajectory like these cell phone things here. It can also just be like a landmark, right? So why do people use landmarks? Because there's a lot of people that took pictures, right? So for example, the Colosseum, people have taken pictures of the Colosseum from like every single viewpoint, right? So that's a very good data set because now you have effectively pictures of the same 3D object from all these different viewpoints, right? So each of those viewpoints is one R1 T1 tuple, which represents one specific point in this SE3. All right. And each point in that SE3 is connected to the two-dimensional image that you took from that point, right? And that two-dimensional image has a bunch of 2D key points in it. All right, so you have a set of 3D points, PK, right, R3, 3-dimensional points. You have a set of camera poses, RITI, N of those. And then you have a set of edges E, and that's what makes it a graph, is that you have these edges that connect them. And those edges connect this camera pose to these specific points, right? The K3D point is visible to the ith camera, so there is different. This camera can't view this first point, and this first camera can't view that last point, but because they have points in common, you should be able to solve this bundle adjustment problem. Right? 2D key point measurement. The bundle adjustment problem consists of estimating points and poses, and here's the actual official formulation of the optimization problem, and we can break this down. So let's go straight into this. So you're trying to minimize, so you're minimizing this thing here, right? So the same way that you minimize your loss function, in this case, you're trying to solve this optimization, which means minimizing this value here. What is this value? This value is a sum over all the edges, so you can see all the edges I, K. So for all the edges between UIK minus pi RIPK plus TI. So this here, this pi, is the projection from the 3D point to the 2D. So it's basically, you're taking this 3-dimensional point and you're projecting it into the pixel space of the camera, right? So there's the 2-dimensional pixel space of the actual camera, right? And you might have key points in that 2-dimensional pixel space, but what you're really interested in is the 3-dimensional position of that key point, right? Which is in the real world, in the real space. So projecting from that real 3D space into the pixel space 2D place is done using this pi function here, which is basically just using that rotation matrix and that translation vector, right? And that's going to give you some two-dimensional point, 2D key point, and that 2D key point compared to the actual position of the 2D key point in your pixel space, right? There's going to be some distance there. If your guess is way off, then the distance is going to be big. If your guess is almost perfect, that distance is going to be small. So when you take that distance and you square it, if it's a small distance and you square it, it's going to be small. If it's a huge distance and you square it, it's going to be even bigger, right? So that squared, that L2 there, makes it even more exaggerated, right? So bigger things become even bigger, smaller things don't become bigger as much. And you sum all of that for all the edges. So if all your edges are pretty shit and all your projections are pretty shit, this number is going to be huge. And that's what it's going to be at the beginning of the process. And then over time, you push gradients and solve this optimization problem. In this case, they're not actually, I don't know exactly if they're pushing gradients. I think they're just using a quadratic constrained quadratic program, aka just kind of classic optimization, implemented the trust region Riemannian optimizer directly in C++ and CUDA. And you can actually go into their, this is the repo here. So you can see it's mostly written by these two guys here, which are the two authors of this paper. And you can see it's like 50% of this code base is C++, 5% of it is CUDA. But you don't that doesn't mean that it's not, right? The CUDA kernel can just be a small part of that, especially if you're running this optimization process for many, many steps. And then the Python is probably just the wrapper code, right? So the code that allows you to kind of load all the images in and then maybe visualize the things, those kind of stuff. But very, very fast. That optimization process is being used to iteratively refine the poses of the camera, right? And you're adjusting, right? That's where the word adjustment in the bundle adjustment means you're slowly adjusting these values, and then over time you will get better and better and better estimates for the positions of these cameras and the position of the 3D point. So you're getting a better and better reconstruction, and you're getting a better and better localization, right? So you're improving both localization and mapping. The sum of squared errors evaluates how well the reprojected 2D points agree with the measurements. An important observation is that the problem can only be solved up to scale. This is always interesting. In computer vision, right, something that's small and close to your camera is kind of the same as something that's big and far away from your camera. So you always have this kind of issue of the scale of the relative scale of the object, right? Because the way that projecting a point into a camera, a 3D point into the 2D pixel space, it's based on, it's always up to this scale, but it does not change the objective value of the problem. Okay. The difficulty comes, this optimization problem, people have been trying to solve this for many, many years, right? The most common one that people use, for example, is Colmap. This is a very popular one. But the issue with this is that there's two problems. First, it's highly non-convex, right? So a convex problem is easier to solve with an optimization because the slope leads you to the right answer, right? So if we go back to this idea of lost landscapes, right? This is a concept that we've talked about for neural nets, but this also applies to other type of optimization problems, right? Where anytime you're doing this kind of iterative optimization, which training a neural net is kind of iterative in that same sense, right? You're basically moving around in this kind of landscape, right? And the shape of that landscape can make it easier or harder to get to your final solution, which is some point in that landscape, right? In that manifold. Sometimes the landscape kind of automatically channels you into that, right? So it's almost like this big basin. So no matter how you move, you end up at the bottom, right? It's kind of like how apparently pandas are lazy. So whenever pandas are eating bamboo on a mountainside, right, they're instantaneously just going towards the bamboo that looks good, right? Maybe in like a couple meters around them, but there's this ever so slight factor where they want to move downhill. So even though they're instantaneously kind of making the choice of moving to the bamboo that's close to them, like over time, they're kind of slowly moving downhill. So that's kind of a similar situation that's happening here, where this problem is kind of like it doesn't have that nice convex kind of property where it's like you just end up at the right place, right? So it's not like if you just kind of try to solve this with a bunch of random arbitrary optimization, you're not going to end up at the right solution. There's a lot. It's going to be, it's non-convex. It's a very kind of, just think of it like this. Think of it like a very gnarly landscape. So you can very easily end up at a local minima that isn't actually the correct one that you want to end up at. Okay. So that's one problem. The second problem is that the number of camera poses and the number of points can range from hundreds to tens of thousands, right? So even just look at this. Look at all these camera poses, all these little red camera frustrums here, these little triangles. These are all, or pyramids, I suppose, are individual camera poses. So just the scale here can get pretty intense, right? And something like Colmap employs an incremental strategy, which starts by reconstructing only 2 views and then sequentially registering additional camera images and an associated 3D structure. Okay. So why is this bad? Well, the reason that that's the case is because Colmap was kind of designed for this type of problem where you have basically like a continuous kind of path that your camera is tracing. So whenever you kind of have this almost like sequential prior, if you want to think of it that way, like you're basically saying, okay, well, I know that this camera, there's going to be another camera right after it, and then there's going to be another camera right after it, and then there's going to be another camera right after it, and there's going to be another camera right after it. Once you have that, then this kind of assumption of, okay, well, I'm going to incrementally do this SFM by saying, okay, well, I'm going to start with the first camera, and then I'm going to do this optimization process where I want to kind of discover this global position of the 3D key points and the camera poses such that they minimize this loss type thing here. Well, doing that incrementally works well if you have this type of camera path. But once you have these kind of situations here where there's kind of like this just random, it's kind of like a Gaussian splat where it's like there's not specific ordering to them. It's just kind of an unordered set of camera poses. Then this kind of incremental, sequential strategy becomes terrible because, first of all, where do you even start? Which one do you start with, right? You don't have necessarily a natural sequence that is there for you to kind of use as an assumption. Give the stream a like, dudes. I appreciate it, 770. Okay. Okay, let's go into really the most important part of this, which is people have been doing this type of papers for a very long time, right? Like this is kind of a classic computer vision paper. There's like probably a million different, maybe not a million, but like thousands of papers that people have written over the decades for these kind of like bundle adjustment, SLAM, SFM papers. But what is different now? What is different about this is we can lift the 2D key points to 3D with learn depth. And this is not new, right? Like we've reviewed other papers that take this concept, but what they mean here is that there is a bunch of off-the-shelf, large-scale, pre-trained monocular depth prediction models, right? So we know a bunch of these already, right? You've probably know some of these, but depth anything V2, metric depth 3D V2, depth pro, uni depth. So these are models that consume an image and output a depth map. A depth map is basically just the same dimensionality as the image in terms of height and width, except for each pixel, rather than having R, G, and B values, it basically has a single number, which is the depth, right? And there's the additional caveat here that there's depth models, but then there's also metric depth models, which don't just give you the depth in some kind of normalized 0 to 1 space, but they give you the specific meters. So they're basically, you give it an image, and these metric depth models have been trained with so much real-world data from depth cameras. They've also been trained with synthetic data where you know the depth because it's a simulation. They've been trained with data sets where the ground truth depth has been labeled. So there's different ways of getting ground truth depth in images, but at this point, we've accumulated enough of that type of data as a humanity that we can train these monocular depth prediction models that'll basically very accurately give you, not super accurately, but pretty accurately give you the exact distance of this point in this pixel here in pixel space from the camera. And that's what this learned depth is, right? So that's pretty useful, right? So now you are not only just trying to solve this problem where you're trying to, okay, you have some 3D key points and then you have some camera poses and you're trying to minimize the offset there, but now you can also use this learned depth to kind of help you, right? You have this kind of additional signal that you can use for this optimization where, hey, actually, I kind of know I have a pretty good idea of what this pixel, how far away that is from the camera. And I have a pretty good idea of what this pixel and how far away that is from the camera, right? So now I have all this extra information that I can use to solve this optimization problem, right? And like I said, this isn't new, right? There's a bunch of the other kind of slammy kind of SFM papers that we've read before have this same concept, right? Of like, hey, learned depth is pretty good now. Why don't we use that learned depth? But this is kind of the most, I think, minimal use of that. I think some of the other ones that we've seen, they don't even try to solve this optimization problem. They basically just kind of feed the entire thing through a transformer and then get they try to end-to-end kind of deep learning the whole thing. This one seems to be a little bit more grounded in kind of the kind of original kind of computer vision math, right? They're not just using gradient descent here. They're kind of using these kind of more classic approaches. They're just using a little bit of the extra signal that we get from these monocular depth prediction models. Okay. Without the reprojection, weighting the squared errors by the confidence values. This is another important point here, is that you have this here, right? So this is basically very similar to what we had up here, but we have this little WIK. So what the fuck is this little WIK? This WIK is a confidence value. So these metric depth models, not only do they give you the depth at a specific point in pixel space for the 2D image plane of this camera, but they can also give you a confidence value. So, okay, what that confidence value tells you is that, okay, I know that this distance to this table right here is 1 meter with a high confidence, but this distance to this door in the background is maybe 10 meters with a lower confidence. So now you can also use that confidence to adjust this, right? So like if you're using this learned depth and the confidence is low, you don't want that to impact your optimization problem as much as if the confidence is higher, right? So that's why you can now not just use the depth, this mu tilde ik, but not tilde. What is that? Squiggle, mu squiggle ik. You can also use this WIK confidence. So now you can see it's a very similar problem as the one we had up here, except we now have these two additional kind of inputs that we're getting from these monocular depth models. Okay. As you can see, a lot of this is math. But why did this paper get outstanding? Why did this paper win the Outstanding Systems Paper Award, right? So it's got to have something, and this is why it won the Outstanding Systems Paper Award. It won it because look at this. Results on the replica dataset. Colmap, while highly stable, is extremely slow, taking over 20 hours for datasets with 2,000 frames. GlowMap, which is some variant of Colmap, improves the speed but still requires several hours for the solving stage and occasionally produces outliers. In comparison, RSolver achieves similar accuracy in just 10 seconds for the same dataset size. So multiple orders of magnitude improvement in the speed of this bundle adjustment problem, right? So that's why they got the best paper award, is because look at this processing time. So this is XM2, which is their algorithm, versus Colmap. Look at this. Colmap doesn't take a lot of processing, but the solver takes a lot of time because you have to do this iteratively, right? It's like doing this sequentially, kind of pair by pair by pair by pair. Look at that, 100.61 compared to 0.12. So like, what is that, 3 orders of magnitude faster? And then look at the, these are different scores. I think I highlighted them here. One of them is absolute trajectory error, and the other one is relative pose error. So basically just metric ways to quantify how accurately you reconstructed or how accurately you solved the localization problem and the reconstruction problem. So the reconstruction is the relative, is that the relative pose error? Absolute trajectory error is probably the localization problem. But the important part here is that it's basically 100 times faster. No, it's 1,000 times faster, almost 1,000 times faster. And it gets roughly the same, right? You can see 0.005 compared to 0.003. So Colmap still a little bit fast or a little bit more accurate here, but just barely, right? 0.004. This one here 0.007. So very, very fast. I think I also wanted to highlight this here. Different depth estimation models. So I think some people on the Discord are pretty into this. So I thought this was an interesting table just to kind of see the speed of these different ones here. So the processing and the solver time for different depth estimation models, 216, 224, 436, 229. So Depth Pro is basically the higher inference, better accuracy. And then Depth Anything Metric 3D and Unidepth are the more similar in terms of processing time and then more similar during accuracy. So if you're using these type of models, Depth Pro is going to give you the best results. Hello, nice seeing you, Hupo. Thanks for joining, Brian Tang. All right. Let's see. Visualization of MIP nerf datasets. This is kind of hard to, like, I'm not going to be able to tell the difference here. Right? The difference is not the quality, it's the speed. So, I mean, I don't know. These look almost identical to me. Like, can you tell the difference between this and this? It's very hard to tell, right? Like, how much more accurate are these than these? This is kind of interesting because you can tell how many times the person went around, right? Because to record this data set, right, the person had a cell phone and then they walked around this thing. So they didn't just walk around it once. They basically walked around it 1, 2, 3, 4, 5 times. 5 times 1, 2, 3, 4. And as they walked around it, they made the camera go higher, which is one of the best scan patterns. So you guys may or may not be into kind of photogrammetry and scanning 3D objects, but yeah, there's this kind of idea of kind of like, how do I actually scan this object to get the most detail? And that's a very good kind of pattern where you kind of start with your camera low and then go all the way around it and then raise your camera slowly as you go up around it. Let's go in Kurt. What do we got here? Oh, this is the actual process. So we have the feature extraction. So this is getting the 2D key points, right? And there's a million ways of doing this. There's like deep learning ways of doing this, and then there's non-deep learning ways of doing this, right? So you can use like SIFT or ORB. These are non-deep learning ways of finding these key points, which are just based on like, I think ORB is like the orientation of color gradients. So basically if there's like these type of corners, right? They're easy to identify between different parts of the image because there's like this dark part and then there's this light part. So it's very easy to identify, for example, the corners of windows or the corners of buildings. And that's how you would classically determine 2D key points. But now there's also deep learning based ways or learned ways of getting these 2D key points where basically someone just fed, I think it was like point map or something like that, or like light map 2D key points. I forget what it was. There was like a paper that we read that was basically a deep learning based 2D key point detector where you just feed the image into this convnet and effectively just outputs like 100 key points that are going to be consistent for the same object regardless of different views, right? That's really what you want out of key points is you want an even distribution of these key points across the object that are consistent across different views, right? So no matter which view of the Coliseum you're getting and you're feeding into these 2D key point detectors, you're going to get the same points, right? So that you can then say, okay, well, this point and this point are the same across these two images. So that means that this 2D point here and this 2D point here are each representing the same 3D point. So that's where you move to this depth estimation. So you take that image, you feed it into your monocular depth estimation model, you get your metric depth. So now you say, okay, well, this point and this point, which are the same points in 3D space, this is how far this point is from this camera, and this is how far this point is from this camera. So now I have a very good idea of where this camera is and where that camera is, right? So now this whole bundle adjustment problem becomes much more tractable once I have this metric depth. 3D observation, here's your actual graph where each camera has some specific 2D key points. And then here's kind of where it gets a little complicated here. Scaled bundle adjustment, lower rank subproblems, global optimality series refinement. That's what these like 5 pages of math here are. The rank staircase. There we go. That's that staircase. The secret ingredient to tackle non-convexity is that we will solve a factorized problem at increasing ranks, like stepping up a staircase. We will start with the lowest rank and solve the problem using local optimization. The local optimizer is the same as the global optimizer, in which case we can leverage the dual SDP to certify global optimality and declare victory against the SDP. Okay, so I think this is kind of like a lower, kind of like a hierarchy of scales here. Yeah, so they probably start and solve this bundle adjustment problem at a smaller kind of a subgraph, and then they slowly there's 2 reasons why that's a good idea, right? One, trying to solve this kind of global graph optimization problem is not going to fit on your GPU anyways, right? It's kind of like too much. So you try to solve a small version of it, right? Maybe just a couple camera poses that are close to each other, and then a couple camera poses here that are close to each other. And the advantage there is that you can also do those in parallel, right? And then once you have kind of better estimates for each of these little subgraphs of your view graph, then you can start to go up into kind of larger subgraphs of your view graph. And then eventually you get to the top of this staircase where I guess you're doing the entire global graph. So that's pretty standard as well. Although I'm sure this specific method that they use here is cool for whatever reasons that I don't understand. Absolutely flowing with information on every live. Yeah, I mean, it's easy. It's like it's not coming from my brain. It's coming from these papers, right? So, all I'm doing is just reading the papers, guys. Training wall clock time. Episode reward. For all manipulation environments implemented in Mujoko Playground, we train with PPO using the RL implementation, and we report reward curves. All environments are run across 5 seeds on a single A100. So this is another kind of important lesson here for people that are just kind of starting on RL, is that these blue lines here, they're all the same except for the random seed, right? So the algorithm is the same, the hyperparameter is the same, everything is the same, except you're using a different random seed, which basically just means that whenever you're randomly sampling data from your replay buffer to put into the batch, whenever you're doing image augmentation, if this is some kind of vision-based environment. So just a little bit of randomness in your RL process, that little bit of randomness effectively drastically changes the outcome, right? Which is one of the weirdest kind of things about reinforcement learning, is that the random seed is actually incredibly impactful, right? I think people that aren't used to RL, this kind of like surprises them the first time they do this, where I feel like with non-reinforcement learning, especially online reinforcement learning, where you're kind of training and then collecting experience and then training and then collecting experience and then training, online reinforcement learning is even more susceptible to this. But they're not used to this idea of like, hey, if it doesn't work, just try it again with a different random seed, and then sometimes it'll randomly work. Like, look at this. Aloha single peg insertion, like this random seed and this random seed, like they're basically almost like functionally identical. It's just that in this one, maybe the first couple trajectories, it like almost succeeded and then it ended up going down this local minima of a really bad kind of policy. But this one here, it didn't succeed. So then it ended up discovering a slightly different kind of approach. And then that approach ended up being way better. So the effect of random seed on RL is just like, it's right here. You can see just how weird that is, that like sometimes you just kind of happen to catch the right experience at the right time, and then you feed it and then you train on it, and then that ends up being more useful. So there's this kind of almost like snowballing effect that can happen in RL. Like, look at this one here. This random seed, very bad. It actually got worse before it started getting a little bit better. See, these are a little bit more grouped, but you still have that effect. Some tasks are a little bit more robust to this. Like, so for example, this one here, spot get up, right? Like all the random seeds are kind of within a little band of each other. That's what the thickness on this is too. So why does this green get more and more wide is because of the random seed, right? So here's the worst seed, and then here's the best seed. You can see here it gets a little, like they converge. So you can see here that the width initially is all the same because it's all shit. And then you have the good seeds are starting to learn very quickly, but then they also plateau sooner, right? And the seeds that are bad don't get good as quickly, but then they also plateau. So eventually all this, the variance kind of, the width kind of goes down and all the seeds kind of converge towards the same optimal solution. But initially there's this kind of huge variance between the different random seeds. All right, what do we got here? We got some unitree quadrupeds. We got some humanoid balancing. We got a little throwback. We got a cube orient. This is actually what OpenAI started with, right? So actually, OpenAI cube. Yeah, look at this. This is super old school. But OpenAI actually originally had robotics division where they basically did this task of like orienting a Rubik's Cube and trying to solve. I don't know if they ever did the actual solving. I think all it did was it really just like oriented it, and then the Rubik's Cube solving was like an actual hard-coded Rubik's Cube solver. Yeah, so it was more like manipulating this block reorientation. But you can see even back in like whatever this was, 2018, they were still, look at this. This is domain randomization, right? So you see here all these different sim environments with different colored hands, right? And those hands also have slightly different inertial parameters, slightly different maybe joint dampening, different variables, different hyperparameters here. They randomized them so that they were able to get this sim to real. So that's exactly what they're describing here, right? This sim to real via domain randomization. So it's not a new concept, right? Of like, hey, sim to real transfer is improved by domain randomization. It's just that nowadays the tools are better, right? So now your simulation frameworks, more and more of them can basically run on the GPU. Not only do they render on the GPU, but you can also have domain randomization at each environment instance on the GPU, which is kind of hard, right? It's like, it's easy to have the same environment with the same textures in parallel on a GPU, but like, for example, here, right, like the background texture here, this is the wood texture and this is a blue texture. That's a different, you could think of it like a texture is just a PNG image, right? So each PNG image that you put on your GPU to render it like this, that's taking up your GPU VRAM. So the more, as the GPU VRAM has increased over time, right, the GPU VRAM in an H100 compared to 3090 compared to a 1080, right? As you have more and more VRAM, you can load more and more of these textures, which means that each batch of training experience that you collect can have more and more variance, right? Because you can have more textures, more different textures per batch. This idea of basically domain randomization within each environment instance. So it's not like you're collecting one batch of experience with one background and then you're loading a different texture and then doing a different batch of experience with a different background, right? You're doing both of those at the same time because you can load both of those textures at the same time because you can fit more texture PNGs into your GPU VRAM. All right, we're kind of getting to the end of the allotted time here. So let's do a little bit of a review. So today's stream was called Feast. We basically went over the winning papers at RSS, which is a robotics conference that just happened. Maybe you saw a bunch of tweets and stuff where people were going, but you go here to the awards section. Pretty much all conferences have this notion of awards, and it's a great way to kind of look and see what the best papers are there. There's a little bit of politics involved for sure. Like, these papers aren't necessarily the best. I'm sure in hindsight we'll go back and say, okay, actually these weren't necessarily the best papers, but generally they're pretty good. The papers that get to these finalists and awards, they're usually pretty solid. So we reviewed the 4 papers. The first one was this one here, Feast. It was basically a robotic assistance device for feeding disabled people. And it was a good kind of like real world demo paper where you kind of see, okay, here's all the different things that we had to do to actually get this to work. I thought the most interesting part of this was the parameterized behavior trees that can be safely and transparently adapted using a large language model. That's a really good idea. I'm totally going to steal that, right? Behavior trees, FSMs, these kind of human designed graphs that define the control flow for a robot, right? So it's like performing this behavior, and I'm going to perform this behavior, and I have a certain amount of retries, and if I fail with this retry at this behavior, then I go back to this behavior, right? And as I was saying before, it's also used for video games. It's also popular to have behavior trees for NPCs in video games. But the idea of modifying behavior trees using a large language model, that's a pretty cool little idea. But also, they won the best paper because they're helping disabled people, which is a pretty nice use case. Very wholesome, makes you feel good. The next paper we saw was this one here, demonstrating Mujoko Playground. So kind of just, there's been a million kind of Mujoko papers. They just kind of keep releasing them, just so you can keep adding new people to it. But it's got all your standard favorite Mujoko people here. And yeah, just basically domain randomized simulation for online reinforcement learning. We talked about this tweet here, how Sim plus RL is going to eat all the teleop plus imitation learning work, right? If you think about the bidder lesson, this makes sense from a bidder lesson perspective because Sim plus RL is just so much more. You can't beat the scale. That was the second paper. Third paper was this one. This was kind of a multi-agent path planning. Constrained Markov decision process, basically getting a bunch of drones to path plan around obstacles, but with interesting constraints. So this constraint of partially observable, which is not super uncommon, right? That's relatively common, but limited communication radius was also pretty cool. 100 secs. I don't know what a sec is, but I appreciate it. Thank you, Aries. But yeah, also this idea, I thought this was pretty cool. The idea of this centralized training and distributed execution, right? Where the policies are being executed but trained centrally with these multi-drone swarms. I thought that was kind of a cool little idea, although there's probably not necessarily novel. There's probably all kinds of papers that did it before this, but solid results, great videos. They did it in sim, and then they also did it in the real world, which is always interesting to see. And then the last paper we read was this one here. Building Rome with Convex Optimization, kind of like a SLAM SFM paper where they basically take kind of the classic SLAM SFM problem and add in the learn depth, which is basically using these off-the-shelf, large-scale, pre-trained monocular depth prediction models to get a pretty accurate metric depth. And with that extra metric depth, you can now have this extra weighted, because you know the confidence, right? These metric depth models not only give you the depth per pixel, but they also give you the weight. And that allows you to get a very good estimate of the distance from each 2D key point to the camera, which if you add that, it makes this bundle adjustment problem easier. And I think part of the reason why they got the outstanding systems paper is because they released this MIT license implemented in CUDA and C++. So it's literally almost 1,000 times faster than Colmap, which is pretty good. So appreciate these lads for giving us that. Zigzag. Hi, Hoopo. Do you think the research on free training based control systems like MPC, LQR still matters in RL era? Kind of like, I mean, that's kind of what this is, right? Like, this is kind of, I don't know. The predictions like this are hard because it's very difficult to know where RL goes, right? Like, that's kind of what I was saying when I was talking about John Carmack is getting into reinforcement learning now. And like, he basically, what it seemed like he was describing is that he basically wrote the entire online reinforcement learning loop in a single CUDA kernel, so that the entire thing like just runs in one big chunk rather than kind of what, for example, these guys do, which is probably they have a replay buffer, they have multiple computers, right? You have like you're storing stuff. So like, I feel like reinforcement learning is going through a very quick transition right now because you have all this money and all this attention and all this interest and all these other smart people from different areas of technology that are coming in and just changing things. So I feel like it's hard to bet against reinforcement learning now because there's just so much happening that I feel like we're going to see some step function improvements. So yeah, but I can't say for sure, right? It's like very impossible to predict the future. Saskia coming in very late, but here. Happy to see you. New to the channel, Antoine. How's it going? Yeah, a little bit of a throwback. I think recently I've been doing some kind of like vibe coding streams, I call them, where I play AI-generated music and I use Cursor to just work on some robotics projects. But this is a little bit of a throwback. We read some papers, which is kind of what this channel used to be about, is just kind of reading these papers. But hope it was useful. And hope you guys have a good weekend. Thank you, Antoine, Saskia, Zigzag, Max, Aries, Kurt, Brian, 770, Ed, 87GN, Kyle Duz, Patrick, Lil KM. Thanks, guys, for hanging out. Have a great weekend, and see you guys later.